We've seen already how to take the derivative of functions where either the base is a variable or the exponent is a variable. So one of the first derivative rules you learn is that whenever you have a variable base but a constant exponent, so the derivative of x to the n, well, then the rule works like this. Derivative of x to the n is n times x to the n minus 1. So this was variable base and a constant exponent. You've also seen that the derivative of a function like a to the x is a to the x times the natural log of a. So this is the other way around. This is where you have a constant base, but a variable exponent. And so, how do we deal with a function like x to the x that has a variable base and a variable exponent? Well, it turns out that the answer lies in logarithms. So let's let y be equal to x to the x. And if I take the natural log of both sides, you get that the natural log of y is the natural log of x to the x. And then we'll use one of our rules of logarithms that says that whenever I have an exponent inside of a logarithm, I can kind of bring it to the outside. So in general, the natural log of a to the b is equal to b times the natural log of a. So in this case, I get x times the natural log of x. Okay, and now we're going to use implicit differentiation. So let's just pan down a little bit here. So, if I take the equation ln of y equals x ln of x, and take d dx of both sides, on the left-hand side, that's a chain rule problem. It's not ln of x, it's ln of y. So you take the derivative as usual, but then multiply by dy dx. Of course, we don't know what dy dx is. That's what we're trying to find in this case. On the right-hand side, that's just a product rule problem. I have a first function and a second function. And so the derivative is the derivative of x, which is 1, times the second function, ln of x, plus keep the first function and multiply by the derivative of the second function. So, in other words, just ln of x plus 1. Well, then, if I want to solve this for dy dx, we get that dy dx is equal to y times all of that stuff. Maybe let me just write it in the other order here. But y, remember, is just x to the x. So really, we have x to the x times 1 plus ln of x. So that's what dy dx is. In other words, that's the derivative of the function x to the x. So we've learned that d dx of x to the x is x to the x itself times 1 plus ln of x. So that's a new sort of formula. It's not really so useful that you want to memorize it, probably. The point really is that if you have any kind of expression where the base is variable and the exponent is variable, maybe they're both functions even, then you can use this sort of same process to find the derivative. Well, let me just maybe show you one example of that. Let's say that you wanted now to find the derivative of, let's say, sine of x to the power of x. So what we'll do is we'll just call the inside function y, sort of the whole thing will be y. Y is sine of x all raised to the power of x. Take the natural log of both sides, so ln of y is ln of sine of x to the x. So it's x times ln of sine of x. Right, this is the same thing that we did before, where we used this fact of logarithms, that an exponent on the inside of a logarithm can kind of come to the outside as a multiplier. Now we take the derivative of both sides. So d dx of ln of y is d dx of x times ln of sine of x. And on the left, again, we get 1 over y times dy dx. And this is just exactly the same left-hand side that we had before. And the right-hand side, again, is a product rule problem. So the derivative of x is 1, and then I keep the function, sort of keep the second function. Then I keep the first and take the derivative of the second. Well, the derivative of ln of sine of x, that's not ln of x, it's ln of a whole thing. So I get 1 over the whole thing times the derivative of that whole thing. So if you want to clean that up, you might say that's ln of sine of x plus, well, cosine divided by sine is cotangent. So x times cotangent of x. And finally, we just want to solve that equation for dy dx by multiplying both sides by y. And y, remember, stands in for the original function, so dy dx is sine of x to the x times the whole quantity that we had on the right-hand side, ln of sine of x plus x times cotangent of x. Okay, so there you go. That's the derivative of sine of x to the x. Okay, so you can just use this process anytime you have a function raised to the power of another function. If you want kind of a fun challenge, try to find the derivative of f of x to the power of g of x.